Thank you, everyone. Welcome to our talk. So today, we're going to give an introduction to NVIDIA adaptive shading technology. It's based on a new GPU feature called variable rate shading, and it's available on our latest Turing-based GPUs. So this talk is primarily contributed by three of us from NVIDIA. I'm a GPU graphics architect. Dimitri Jadan is a dev tech engineer and sitting next to me. And also Matthew Johnson, who unfortunately couldn't make to the GTC trip this year, so we'll be presenting for him. So here's the agenda. First, I'll give a brief intro to variable rate shading. Then I talk about how it can be used in common APIs, and also the similarities and differences between the different APIs. And then I'll cover the intuition and some details about the NVIDIA adaptive shading technique, which includes two components, content adaptive shading and motion adaptive shading. I'll talk about how NVIDIA adaptive shading was implemented in the game Wolfenstein 2, and also some lessons we learned. And at the end of the talk, we'll give a demo of the game to show the technique in action. So let's look at this new GPU feature first. If you were in Microsoft VRS talk on Wednesday, this part will be a quick recap for that technique. So the reason why we developed variable rate shading is the increasing demand of the pixel shading costs in today's games. This is not only driven by the need of the enhanced realism and the special effects, but also pushed by the fast-moving standards of the ultra-high resolution and frame rates. So this caused us to re-examine the rendering pipeline and look for inefficiencies that we could improve from the hardware side. One problem with the pipeline we've been using is the lack of level of detail control in shading. Instead, we run shading at the same rate everywhere, regardless of content. And this clearly has caused some waste, like what I'm highlighting in this image. You can, yeah. So we introduced this new feature on the NVIDIA Turing-based architecture called variable rate shading, in which we can use to reduce shading rate on a fine-grained control. And it's available today and supported by major APIs. The basic idea of variable rate shading is pretty simple. So we will vary the shading rate across the screen while maintaining a fixed visibility sampling rate. And before I can explain how that works, let's take a step back and look at an existing common approach that we've been using to save shading costs, which is reduced resolution rendering. So in that, we render into a low resolution frame buffer. That means the rasterization happens in low res and shading happens in low res. Then we upscale the result to full target resolution. And this clearly does save us some shading costs. But the downside is that you can only shade things at a fixed rate, and your visibility sampling rate is lowered as well, which causes the jagged edges. With variable rate shading, we directly rasterize the scene to a full-size render target. It's the pixel shading stage that we introduce this fine-grained control of the shading rate. So the developer provides a shading rate image, which is 16 by 16 times smaller than the render target. And each entry or texel in this image encodes the shading rate of a 16 by 16 screen block. So in this example, the top half, which are the red tiles of the image, is set to shade once per 4 by 4 pixel block. And that means that we can reduce the shading rate by 16x. And the green tiles are set to shade once per 2 by 2 pixel block, which means 4x reduction. And finally, the white tiles are set to shade at a native rate. There is no reduction in shading rate. So the resulting image contains the perfect edges sampled at the pixel rate, while the shading rate is varied based on what is dictated in the shading rate image. And we don't need to manually upscale the coarse shaded regions. It's all done by the hardware automatically. Here we can take a closer look at how coarse shading or variable rate shading is done. So in the traditional full rate shading, when a primitive is rastered, we shade at all covered samples. And now in variable rate shading, let's say that we are shading in a 4x4 mode, which means every 16 pixels share one shading result. And in this mode, the GPU will shade once in the center of each 4x4 tile pixels, and then broadcast the result to all covered samples in that region. And other than that, all visibility calculation like coverage or depth test, they're all done exactly the same as in 1x1 case. And also note that there are some cases the shading location might be outside the triangle. I'll talk about that special case in a second. Well, in a few slides later. So here are all the shading rate options that we support. Other than the fixed, other than the square-shaped 1x1, 2x2, and 4x4 modes, we also support the rectangular coarse pixel sizes like 2x1 or 4x2 modes. And also note that this X-shaped thing is part of the stretcher of that chair, so its appearance doesn't change because it's the shape of its geometry, and the visibility sampling rate of the geometry is always maintained. Okay, so our goal is to save some shading costs when lowering the shading rate. This is going to help reduce shading costs on forward passes, like the base passes in forward renderers. And particularly, if the performance bottleneck of the forward pass is in the shading unit, this is going to bring us massive savings. But it won't help if the draw is frame buffer bandwidth limited, like when you're doing particle blending, or when this geometry is CPU bound. It also won't help if the primitive to pixel ratio is close to or bigger than 1, like when you have over-tessellated geometry. But it shouldn't hurt in that case either. And you might have noticed already that VRS, or variable rate shading, bears much similarity to MSAA, which offers a fixed ratio between the shading rate and the visibility sampling rate once a render target is chosen. And in fact, with VRS, we now support the full continuum between shading less than once per pixel, or coarse shading, and shading more than once per pixel, or super sampling. So these modes can be mixed on the same screen with 16 by 16 tile granularity. Here on the left, I'm showing the 12 modes that we support. So you can choose between 2 to 16x super sampling to 2 to 16x coarse shading. There's also a mode to tell the rasterizer to call the geometry in the tile. So, and note there is a limit of 16 pixels per samples that a shading result can be broadcast to. So if you use 1XA, you can use 4x4 coarse mode, no problem. But if you use 4XA, then you're limited to 2x2 coarse mode max, because each pixel now has 4 samples. And so you can only broadcast shading to 4 pixels, and that involves 16 samples total. And also, like MSAA, coarse pixel attributes are interpolated in the pixel center. So it is possible that you can shade outside the primitive. It's usually not a problem, but if it is, you can add a centroid modifier to any attribute, and it will be evaluated at the centroid of the carved samples. Again, like MSAA, gradients are affected in the centroid mode, so you might need to adjust it manually if you're doing something like a mipmap texture fetch. Also, similar to MSAA, the coverage mask can be modified in the pixel shader. This is useful when you're shading coarse, but you would like to do alpha tests per pixel in the shader so that your alpha tested geometry won't look blocky when it's shaded in coarse mode. Since the app can specify arbitrary shading rate patterns, there are many use cases that can leverage VRS. Here are some examples. You can do foveated shading, where you reduce shading in the periphery of the view based on the gaze point. You can do lens match shading, where shading rate is configured to match the lens profile. You can also do adaptive shading, which is the focus of the later part of this talk. And you can also do selective supersampling, where the supersampling is turned on for places that would have the shader aliasing. Okay, let me spend a few minutes to talk about the common API support for this new feature. This is the typical usage pattern for enabling VRS in an app. So the app first queries VRS support. If it is supported, then it can create an 8-bit unsigned integer shading rate texture, and then it fills it with the desired shading rate pattern. And after that, the app can enable VRS in the graphics pipeline and bind the shading rate texture before it can issue any draws. So there's nothing need to be changed to the draw calls. No data or shading changes necessary. The code we need to add to the engine is fairly minimal that is listed here. And this is how you do it in the DX11 without NV API. So we provide functions that you can call for each step that I listed before on the previous slide. For shading rate texture, you need to create and bind a special type of view similar to shading resource view or an unordered access view. And there's an HLSL function that you can optionally use to access a shading rate in the pixel shader, but only if you need to do some shading rate aware tricks. And finally, you need to program the shading rate lookup table per viewport. So this shading rate lookup table is a programmable table for the hardware to decode and map the data from the shading rate texture to the actual shading rate mode. This table provides extra flexibility. For example, you can program this to achieve a per viewport shading rate configuration or do something even smarter. Using VRS in Vulkan is very similar to DX11, except that you need to set this special usage bit when creating the shading rate image and its view. Also, like in DX11, the app has to program the shading rate lookup table per viewport. In Vulkan, this is called the shading rate palette. One thing specific to Vulkan is that the app needs to explicitly manage resource state transitions. So an image memory barrier has to be used to set the correct access bits and the layout bits for the image to be bound as a shading rate resource. The details can be found in the spec. And again, using VRS in OpenGL is very similar to the DX11 or Vulkan. You don't need to set the special bit or the resource layout. The driver takes care of it. Now in DX12, the API is designed to abstract this feature from multiple IHVs. So therefore, the feature support input into multiple tiers, which you can query. On Turing GPUs, we support tier 2, which is top level available today. There's also a special concept in DX12 called the combiner function, which you need to specify in order to enable VRS. The combiner is a fixed function mechanism to combine 3 different sources of shading rate. So there's first a base shading rate, which can be set per draw call. And next, the vertex or geometry shader can set a primitive shading rate through a special attribute in the shader, which can override or be combined with the base shading rate using one of the functions on the right. And finally, the shading rate image can provide a third input, which can again override or be combined with the passed-on shading rate. So these combiners provide additional flexibility for the app to implement adaptive shading. Here's the result if you query VRS support on Turing GPUs. We support tier 2, which allows primitive and image-based shading rates, plus a few additional features. And we support either primitive shading rate or viewport indexing with image-based shading rate, but not both at the same time, because this is rarely needed for the application we consider. Here, I'm summarizing some major differences between DX12 and other APIs. You can set per-primitive shading rate more easily in DX12. In other APIs, you can do it by using multiple viewports programmed to different shading rates, but it's not as straightforward as in DX12. The shading rate combiners are not directly available in other APIs, although you can program the per viewport shading lookup table to get the exact same behavior. Also, DX12 doesn't support hybrid supersampling yet. It is available in other APIs now. And also, DX12 has a fixed coverage mass sample order and the shading rate palette. So it provides a more fixed function exposure of these hardware features. DX12 support will be enabled on Windows 10 build 19H1. For further information, there is a spec, and there are 2 excellent Microsoft talks on this topic on Wednesday that you might want to check out later. Now we have learned enough about variable rate shading. Let's dive into the NVIDIA adaptive shading technique. It has 2 building blocks, content adaptive shading and motion adaptive shading. Let's look at content adaptive shading first. The motivation of adaptive shading is image quality. Like any approximation, reducing shading rate can introduce some error to the results. So to achieve the best image quality, we should only reduce the shading rate where the error is not visible. We found that the visibility of the error depends on 3 factors: the spatial frequency and the contrast of the error, and how fast the object moves. Let's look at the first 2. And here's a visualization chart called the Campbell-Robson chart that shows how spatial frequency and contrast affects sensitivity in the human vision system, or HVS. Assuming the vertical bands are some error signal, we can see that the spatial frequency and contrast has some interesting interaction when affecting visibility of that signal. In fact, we can draw a curve that separates the visible and the invisible area. You've probably noticed that on the right-hand side, the higher frequency that signal has, the more contrast range of that is invisible. And not surprisingly, the error introduced by lowering the shading rate is also in the higher frequency range. So if we manage to identify that region above the curve and reduce the shading rate in there, it won't cause a visible image quality loss. That's exactly how content adaptive shading works. And here's a side note. Adaptive shading works better when the target is in extra high resolution, like 4K. One reason is that with higher resolution, the pixels are smaller, and the pixel size details are in higher spatial frequency, which means our eyes has lower contrast sensitivity in them. That gives us bigger headroom to lower the shading rate. Another reason is that the same content we have a higher pixel to primitive ratio on a higher resolution display. That also improves the VRS performance. So we need to predict how much error we are going to get when shading in lower rate for each screen tile. The best data for this, the best data for us to do this analysis is the previously rendered frame. So we run a shading rate compute pass that takes the previous rendered frame as the input. And for each 16 by 16 tile in the current frame, we reproject the location to the previous frame and compute one shading rate by analyzing the matching block in there. The shading rate is then written to the shading rate texture, which is later used by the forward shading pass to actually shade in the current frame. This is the basic flow of our approach. So how do we predict the error using the image tile from the previous frame? And remember, there are multiple shading rates modes. We could blur the tile based on different block sizes and compute the differences against the full rate mode, but that's not quite efficient. So instead, we propose a more efficient algorithm to estimate the error. Let's first step back to look at a simpler 1D case where we have a line of pixels. We compute the error in luma channel only because that's a channel that our eyes has the highest contrast sensitivity. We have the result from the full rate shading, and assuming the shading signal is properly anti-aliased, then in half rate shading, every pair of pixels share one shading result, which is the average of the corresponding 2 pixels in the upper row. If we take the absolute difference between the 2 rows per pixel, then we get these terms, which are exactly half of the absolute luma derivatives per each pair in the first row. If we sum those up and normalize, we'll get an average half-rate shading error in this group. The average error in a tile can be an arithmetic mean, a mean squared error, or a max of the derivatives. One thing to note is that we compute the derivatives at all pixels, not just every other pixel. One reason is that we want a stabilized result, not something that will change drastically when the image is shifted by 1 pixel. Another reason is that if we only count on the derivatives at every other pixel, then the previous frame's derivatives would vanish when it was already shaded in half rate. Using the derivatives at all pixels gives us a more robust estimate in this case. And now we have the 1D case. To extend this method to 2D, we compute the derivatives in both x and y directions. And we compute that for all 16 by 16 pixels in the tile. So for each dimensions in x and y, we can enable half-rate shading when the estimated per tile error, which is denoted by EH, is smaller than the threshold. Can we set the fixed threshold here and call it a day? Unfortunately, this is not a good idea. So there is a very basic perception theory called the Weber-Fechner law. It says that the just noticeable difference between 2 stimuli is proportional to the magnitude of the stimuli. For our case, the stimulus here is the luminance, and the law basically says that the threshold for just noticeable difference should be set proportionally to the base or the minimum luminance level in that region. So that's what we should set the threshold to. And that's basically saying the brighter that luminance is, the more error our eyes can tolerate. And that's how we decide when to turn on half-rate shading for each dimension. For quarter-rate shading, we could repeat the same process, but it's not going to be efficient. So instead, we compute an approximate error term, EQ, which is 2.13 times the half-rate estimate term we computed before. So this magic number was derived by using signal processing theories to analyze the difference in frequency space between half and quarter-rate shading. If you're interested in the details, we've published a paper this year in i3D, and there is a page of equations in there for deriving this. With this new term, you can simply test it against the same threshold that we had before to decide whether you should enable quarter-rate shading or not. So to summarize how we do content adaptive shading, for each 16 by 16 screen tile we project to the previous frame, we compute the per pixel luma derivatives in x and y, and then we compute the tile error estimate, EH and EQ, based on the luma derivatives in x and y. Then we compute the just noticeable difference error threshold from the screen tile, and we can decide shading rate in x and y by testing error estimates against that threshold. This is how content adaptive shading works. Now let's look at the motion adaptive shading. The theory behind motion adaptive shading is that the motion blur can help hide some of the error introduced by VRS. There are two common sources of motion blur. One is the engine-simulated motion blur effect, which everyone knows about. There is another one, which is the LCD display persistent blur, which not everyone is familiar with, so let's talk about that. The LCD persistent blur is an artifact that is common on most LCD displays. So if you look at the left side, when our eyes is following a moving object in the real world, the image of that object on the retina is static. On the right side, because the display can only refresh at the fixed intervals, the displayed object has a jerky motion. Our eyes are still trying the best they can to follow the object in a linear motion, but on our retina, the image is not stable. This causes a blurry image. The effect is visible on both 60 Hz or 120 Hz display. And there's a website called testufo.com that has a real-time demo of this effect that you can check out. And we know that both types of motion blur can reduce the high-frequency details on objects, which is exactly where the VRS error lies in. So the faster motion we have, the wider motion blur we'll get, and the less VRS error we'll see, which means we can lower the shading rate more aggressively. Here I'm showing a simple example of this effect. The first row is shading in full rate, and the second and third rows are shaded in half and quarter rates in the horizontal direction. The image right in the middle adds a small motion blur to the half-rate image on its left, and it looks very similar to the one above it, which is shaded in full rate. The bottom right image adds more motion to the quarter rate image, and the blur almost hides all the error except along the high contrast contour of that UFO thing. We want to exploit the motion blur so that we can lower the shading rate even more without sacrificing image quality. The way we do it is to factor the motion influence into the estimated error that we had in content adaptive shading, because this error is truly reduced after applying the motion blur. So we already know that motion blur scales down the estimated error per tile. We approximate that scale with two functions, BH of V and BQ of V, for half and quarter rate shading. Those two functions only depend on the motion speed V of the tile. We compute these two functions numerically across a full range of motion speed, and then we fit two closed form functions so that we can use them easily in a shader. Again, the details can be found in our paper for how to derive them. After we plug those scales back into the content adaptive shading algorithm, we now have a fully unified content and motion adaptive shading. And by the way, the per tile motion speed V should be computed as the minimum motion vector across the 16 by 16 tile, because we need to be conservative. If anything, the tile is not moving, we should consider the whole tile as static. In this example, you can see how the new motion scalar affects the shading rate pattern. The top right image visualizes the shading rate using content adaptive shading only. And the bottom right image shows the content and motion adaptive shading. You can see that most of the tiles got promoted to 2x4 or 4x2 pattern, which is visualized in yellow, because there is a strong camera motion in here. There's also one additional thing that is worth mentioning here. So a major benefit of motion adaptive shading is that it delivers high frame rate when it's actually needed. By that I mean, when things are moving, motion adaptive shading gives you smoother motion, which is just what you need in here. And also, a common problem in today's engines is that when the camera is moving fast, the motion blur effect slows the whole frame down because wider blur takes longer to compute. With motion adaptive shading, you can counteract that effect, which helps to stabilize the frame rate. Okay, next, I'll cover how we implemented NAS or NVIDIA adaptive shading in the game Wolfenstein 2. This is a highly successful first-person shooter game developed by Machine Games, and it was released in late 2017. We helped Machine Games to integrate NAS into their ID Text 6 engine, and the feature was released around Christmas last year as a patch. And the patch received very, very good reviews among the critics. Dimitri is the main guy behind this fabulous work, and he'll show you a great demo at the end of the talk. So NAS integration in Wolfenstein 2 is based on the VRS extension for Vulkan. It brings us an average of 2x performance boost on 4 shading passes, which translates to from 2 to 20% savings in the whole 4K frame. This is extra performance almost for free, and it's on an already heavily optimized engine. And by free, I mean there's very little code or pipeline changes to the engine, thanks to the simplicity of the algorithm, and there's barely any visible image quality loss, even with close examinations. And this has been a strict image quality target from the beginning when we developed this. And by the way, the benefit of NAS is higher on even bigger display resolutions like 5K or 8K. So this makes them more feasible for a wider range of hardware. Here's a screenshot with NAS off. It is running at 116 FPS. When we turn NAS on, it is running at 127 FPS. Apologies that there are 2 frames, those 2 frames are not exactly the same. There's some lighting changes on the weapon on the ground. But also, I'm not expecting you to see any image quality difference on this projector. Even on a professional 4K monitor, they look almost identical. What I want to show here is the shading rate visualization. And you can see how many tiles got massive savings on this frame. And this is a static frame, not even including motion. The green tiles got maximum 4x savings, and the yellow tiles got maximum 8x savings. So now here's the overview of the algorithm. We'll break the NAS shading rate compute algorithm into 3 passes. The first pass computes the per region NAS data. It runs on the previous frame's asynchronous compute channel, since it relies on the previous frame's final color output. And then the second pass and the third passes run on right before the current frame's 4 shading passes. And they reproject the data from the previous frame to the current frame, computes the per tile shading rate, and then smooth out the shading rate image. There's some architecture-aware optimization that we designed for NAS. Since shading rate calculation is primarily a data reduction task from 16 to 16 pixels to 1 shading rate, we need to be very careful in the implementation to make it efficient. So the way we do it is to process the entire 16 by 16 tile in 1 single warp, which is 32 threads on our architecture. Each thread in the warp manages a 2 by 4 block of pixels, like what I'm showing on the right. And within the 2 by 4 blocks, each thread just does the reduction operation on registers. And then among all the threads, reduction is done with atomics, which our compiler would happily optimize into intra-warp shuffle instructions. This avoids the expensive global memory or shared memory atomics. And all passes together at only 0.2 milliseconds on a 4K frame. And by putting it into the Xsync compute queue, the overhead is completely wiped out. So this is pass one. And in pass one, the most important NAS data we compute is the luma derivatives. We first need to convert the per pixel final sRGB color into linear luma value. Then we compute the per pixel luma derivatives in X and Y. And as I said in the last slide, each thread computes the derivatives for a 2x4 block. We've decided to save a few texture fetches and half of the math operations by computing only half of the derivatives in a checkerboard pattern, like what I'm showing on the right. The black bars connecting neighboring pixels are the derivatives we compute, and the green pixels are the ones that we actually load per thread. And remember, we need to correct the sensitivity of the error estimate using the Weber-Fechner law. Here, we divide the luma derivatives by the minimum luminance of the pair plus the brightness sensitivity term. The brightness sensitivity terms correct the sensitivity on the lower luminance end, where the Weber-Fechner law no longer holds. And this term has a configurable constant, and it also depends on the minimum lumens of the block. Now, each thread has the derivative in a 2x4 pixel block. The first 4 lines in this code snippet just compute the sum of them for both X and Y. And then we use atomic add to do the warp level reduction. We save some cycles by concatenating the X and Y derivatives into a single uint32 variable, so that the 2 atomic adds can be merged into one. Other than luma derivatives, we collect some additional material properties per tile, including smoothness and specular reflectance. This data is needed in pass 2, and I'll explain about why we need that later. And by the way, for this data, we are also taking the checkerboard pattern to save some bandwidth. Now in pass 2, we are going to reproject the data we computed in pass 1 to the current frame. If we don't reproject, we have the 1 frame latency problem, where the data computed in the previous frame would misalign with the current. Here's an example. If the features in this image are moving down, if you don't want these coarse blocks to overlap with the fine details in the new frame. The way we compute reprojection is to find the furthest point per tile in the frame using depth from the Z prepass, and then reproject this 3D point to the previous frame using camera matrices from the previous and the current frame. Using the furthest point will give us the minimum motion vector in the tile. And this doesn't consider dynamic objects, but for a conservative estimate, this works good enough. With this vector, we can fetch the data we computed from the previous frame, and we also use it to determine the motion influence for motion adaptive shading. There's one problem we haven't talked about. The specular aliasing in VRS can look bad, especially when post-processing is done in HDR. This is because a high energy block of specular can get smeared or bloated into a big blotch after post-processing, and it's usually not temporarily stable. There are 2 types of problems that we need to tackle here. The first problem is shimmering in slow motion. This is because the engine has HDR motion blur, but we need to post-tone mapping color results from the previous frame, so the image we got is already motion blurred. This causes our algorithm to underestimate the derivatives when there is motion. In the example on the right, when there is slow motion, the surrounding low shading rate regions will creep into the center, but the motion blur is not enough to hide the error. The workaround we use is to identify such surfaces by using a mixture of smoothness and reflectance coefficients, and then increase the error sensitivity under slow motion. The second problem is the feedback latency problem. The TAA has a tendency to retain the history results. So when there's fast motion that suddenly stops, it's going to take a while for TAA to refresh. And that causes NAS to stuck in lower shading rate for extra long time. Fortunately, this only causes problem on smooth metallic surfaces. So our workaround here is to identify those places using material properties again, and then increase the error sensitivity in there. Here's an example of those special regions. The red region contains high-frequency specular that should never get its shading rate reduced. The green region can get its shading rate reduced, but only when there's no motion. The second pass outputs a shading rate, which we can directly use, but it can be unstable between frames. The problem usually happens at the fine and coarse region boundaries, especially when the shading rate in the neighboring tiles differ by more than one level. And a common solution to any temporal stability problem is to add exponential smoothing, but we quickly found that this introduced a bad latency to the shading rate. The actual solution here that works is spatial smoothing, but it can't be a regular blur. We've actually tried a simple 3x3 blur, which turned out to be a bad idea because coarse tiles can lead astray the fine ones. Instead, we implemented a special blur that only allows the fine tiles to blend into the coarse tiles, but not vice versa. This turned out to work very well, and it is a tiny pass that costs almost nothing because it works on the shading rate texture that is 16 by 16 times smaller than the render target. Here's a summary of our lessons learned while implementing NAS in Wolfenstein 2. We all know that HDR motion blur is more physically correct, but it makes a NAS harder to do since we lost the clean, unblurred, and tone matte version of the previous frame. And we need to avoid any latency in this technique. So if you render a frame using stale shading rate data, then the artifact might be noticeable. We've also tried to improve the VRS blockiness and aliasing by using a special modified TAA kernel, but we didn't use that in the end because of the complexity to implement that properly in the engine. And finally, if the target format is 1080p, then implementing NAS needs some more tuning because our eyes have higher contrast sensitivities with larger pixels. Now it's time for us to see the demo. So this game is actually rendered in 4K, right? Yeah, so maybe it's somewhat downscaled by the projector, but on this machine it's rendered in 4K and also on this monitor. So you can see that shading rate visualization is turned on. And when you move the mouse, you can see the shading rate is increased because of the motion blur. Yeah, you can try to.
The floor here is a very good example how it works. So it's
Oh, yeah, okay, thank you. So the floor is a very good example for better understanding how it works, because it's, let's say that details have very high frequencies due to these small things, but due to lighting conditions allows us to reduce shading rates in shadows. The projector is good, of course, but it's barely visible. At least I see it on the screen, and I guess it's not visible to you. But actually, we are applying the worst shading rate, which is yellow. It's not clear here, but I will explain. So yeah, transparent tiles mean regular 1 by 1 shading, so it's regular shading. Blue tiles have 1 by 2 or 2 by 1, so it's 2x reduction in actual shaded samples. Green tiles have size 2 by 2, and yellow, the worst thing, have size 2 by 4 or 4 by 2. I don't know, is it visible? Oh yes, it's barely visible. White dots mean a tile orientation. It's hard to say right now, but without dot it should be. Okay, let me check it.
Yeah, when you move left and right, you see that there's always a dot because it's shaded in 4 by 2 mode.
Yes, so the system, of course, tries to orient tiles according to the worst direction, and it's based on two factors: motion and color information. For example, when we compute color derivatives and there is no motion, if a worst color derivative is along x-axis, then of course we are trying to align tile along x-axis. So it will be some kind of a 2 by 4, and vice versa, of course. The same is applicable to motion. So as you can see that when you move mouse from the left to the right, mostly all tiles get one orientation, and when I move it up and down, there are only a few dots, and it's based mostly on color information and no motion. The entire thing is completely adaptive, and probably it's worth noting that despite that feature is completely free in terms of performance, but we definitely need to spend some time on the GPU to calculate shading rates. And how long does it take? On 2080 Ti, it takes 0.2 milliseconds at 4K, and I need to say that somewhere around 0.1 millisecond is hidden by Sync Compute, so it's almost nothing. But of course, some overhead is here. So we put a lot of efforts trying to optimize it, like using a single warp for reduction, omitting a couple of probably unneeded samples, like Lei just explained. I can move around.
We also have a demo in the booth. There's probably 40 minutes left before the show floor closes.
Yes.
If you have interest, you can go to our booth and try it yourself.
I would like to demonstrate some interesting effects, like when camera motion is very strong, then you can see some kind of latency. But actually, it's not latency. If out-of-bound sampling is detected, then obviously we just don't have information needed for us, and we can't use color information and motion. Color information just not available, but interestingly, that motion information which is available in the current frame, we can't use it. Why? Due to mega texture. So you know, Wolfenstein is based on ID technology. It's very smart engine. It uses mega texture, and it's based requests for mega texture based on, let's say, some kind of feedback from the previous frame. So when we reduce shading rates, the engine on screen borders under motion, the engine can detect that new region appeared, and according to color derivatives, according to derivatives which are dumped out in forward plus, they will start streaming proper MIP map level from mega texture. And it was not obvious initially, but we realized that we are not allowed to modify new regions, newly appeared regions on the screen, because it leads to significant increase of time needed to get finest level of mega texture appeared on the screen. So it just greatly affects latency, and it's not what we want.
All right. I have one more slide left,
Oh, yeah,
and
okay.
then we can switch to Q&A. So to summarize, variable rate shading is our new GPU feature available on Turing and supported by major APIs. Integrating VRS needs very little engine code change, and there are APIs that offer flexible options to make it easier. And we also proposed NAS to unlock the extra performance without perceivable quality loss. It provides 2x and up to 5x performance gain on forward shading passes. It applies a perception theory to best locate and avoid overshading. And it also helps to achieve the best performance in motion where it used to be problematic. So we've received help and support from many folks and parties. Otherwise, we couldn't make this happen. So we would like to express special thanks to them. And that's the end of our talk. We're happy to take any questions.